So in this video, we're going to talk about interpolation. Interpolation is a name for essentially filling in the spaces or the gaps between given data points. So let's suppose we're given a set of data points where we have, some measurements taken at let's say, time 1, time 2, or x position at 1, x position 2, x position 3, x position 4, and so on. And at each of these positions, x positions in space, let's say we have measurements f of x. This is f of x1, this is f of x2, f of x3, and so on. So we have measured the values at these discrete x locations, but let's say we are wanting to find out what's the value of f of x at a position that which was not measured, for example, at x equals 1.5, right? So we're asking, what is f of, say, 1.5? In this case, we don't have it. The measurements that we have only have the measurements of x at some integers, let's say, and we don't have it. So the point of this video is to learn how we can write a formula for f so that this formula will contain a function, will describe a function, and this function will pass exactly through this given points, and in the middle it will do what it does, right? And different kinds of functions, different kinds of strategies will give you different answers. Today we're going to learn how to essentially fill in these gaps with a polynomial, but in other videos we're going to learn how to do this with other functions. So first thing we need to do is find a name for the given data, right? And we already established that the given data will be written as f of x, where x will be given at location 1, 2, and so on, perhaps all the way through some point n. In this case, we have, 4, 5, 6, 7, 8, 9, 10. So we have 10 measurements. And so we have 10 values for f of x. And we're going to seek some function, which maybe we'll write as v instead, that when I evaluate this v as some k, this will be equal to f of k, where k will be our integer values. But I can also plug in whatever value of x that I want. Because we'll have a formula for that, right? And the formula that we're going to use will be, for v of x, will be essentially the formula for a generic polynomial. For example, v of x will be given by a sum, say from index variable p, so p for 1 through n, of some coefficients, which I'll call c of p, right? So this will be the c here will be an array of coefficients times the value x at to power p minus 1, right? So at first this formula here may be looking a little bit strange, so let's take a look. For example, let's say when n equals let's say when n equals 2, for example, then we can evaluate v of x to be sum over c 1, x to the 1 minus 1, so this is x to the 0, plus c2, x to the 1, right? So x to the 0 is 1, so we're just going to have c1 plus C2 times x, right? So this is the equation of our line. We can take a look at other possibilities. When n equals 3, v of x will be c1 x to the 0 power, c2 x to the first power, plus c3 x to the second power. So this is a quadratic function. So this is a generic formula, right? So we can evaluate this polynomial for any degree n that we choose. And in this case, what we're doing is we are going to set the n to be precisely the number of points that we're given, right? So we're given a data, an array of data that we'll call f of x. We're evaluated at 1, 2, 3, and so on. And we're going to set our value of n to be exactly the number of data points that we have. So how do we do this? Again, the basic requirement is that vk equals to f of k, where f of k for k equals 1 through n is given. And I argue that if we simply do this and write out the function for v of k, plugging in the polynomial formula over here, we will end up with a linear system of equations, which we just finished studying. So let's do this. Let's do it for, let's say, the first element, right? So we have to say that for k equals 1, f of 1, which is given, has to be equal to, here's a polynomial again, so we just have to plug in this formula. This has to be equal to c1, here we go, c1 times x to the 0, right? So x in this case is going to be evaluated at 1, so 1 to the 0, plus c2, 1 to the first power. I'm using a different index for c2. I should be careful. I should be consistent here. So this is c2, 1 to the first power, plus c3. Let's just evaluate a few more terms. 1 to the second power, plus all the way to c of n, and 1 to the n minus 1 power. Right? So that's the first we evaluated f of 1, right? So let's do k equals 2 now. So now we have f of 2. This is going to be c1, 2 to the 0 power, right? It's silly to write 2 to the 0 power. Of course, 2 to the 0 is 1, but let's just follow along for a bit. This is c2, 2 to the first power, plus c3, 2 to the second power, plus all the way to cn, 2 to the n minus 1 power. Right? And of course we can do, let's do one more just to be thorough. F of 3 equals c1 to, 3 to the 0 power, c2, 3 to the first power, c3, 3 to the second power, plus all the way to cn, 3 to the n minus 1 power. And of course, we can keep doing this, and I'm not going to do all of them. I'm just going to finish off at k equals n. So we have f of n, which is again given. It's going to be c1 n to the 0 power plus c2 n to the first power plus c3 n to the second power plus dot 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 plus cn n to the n minus 1 power. So let's stop here for a second and let's take a look and try to interpret this with respect to what we learned about linear systems just a little while back. If we look here, we can write this set of equations, right? We have here, we have how many equations? We have n equations, okay, 1, 2, 3, all the way to n. How many unknowns we have? We have these coefficients c here, which are unknown. How many do we have? N. So we have n equations and n unknowns. Right? So we can borrow the trick of rewriting this whole system of equations the following way. We will write this remember we used to write a b vector, so I'm going to take all of these values here, all these f's, and write this as a vector. So I'm going to call this vector f. And of course this vector is going to belong to the set of real values in n dimensions, right? So this is a vector, so let's write what this vector means. F will be our vector of f1, f2, all the way through fn, right? This is our vector f. Likewise, we're going to call a vector c of coefficients. These coefficients will also belong to the set of real valued vectors. And c, likewise, will be defined as the value c1, c2, all the way through cn. And these are unknowns. This vector, right, by the way, is our given data. It's known. So finally, the piece that we're still missing are these values here, right? The 1 to the 0, 2 to the 0, 3 to the 0, n to the 0. Of course, these are all ones. Here we have 1 to the first power, 2 to the first power, 3 to the first power. Of course, these are just 1 through n, right? Here we have 1 squared, 2 squared, 3 squared, and so on. These values will become our matrix. We used to call this matrix A. So let's write a few elements of this matrix. So again, this is going to be 1 to the 0, 2 to the 0, the first column, all the way through n to the 0. And that's going to be our first column. The second column will be 1 to the first power, 2 to the first power, 3, and so on. Right, so we'll say 1 to the first, 2 to the first, all the way through n to the first. Let's write the third column. This is going to be 1 squared, 2 squared, all the way through n squared. And of course, we keep doing this all the way until until 1 to the n minus 1, 2 to the n minus 1, 3 to the n minus 1, and so on. So let's write this down. 1 to the n minus 1, 2 to the n minus 1, all the way to n to the n minus 1. So what do you know? In the end, we can now write this this whole system here of equations, right, as a system of linear equations where we have essentially our vector A, C, a matrix A times vector C equals our vector F. Again, this matrix A is given by your polynomial values being evaluated, right? We started with the premise that we were going to fit a polynomial of this type to our red points here, our given data. So that is where this matrix is coming from these values of the polynomial. This vector here of C is our vector of unknown coefficients of the polynomial. And essentially F here is our data given. Right? And the basic rule comes from the fact that we must have the same number of equations and unknowns. So we have to have n equations and n unknowns. If we have this rule, then the linear system will have a unique solution. We're not going to prove this. This will come in a more advanced linear algebra class, for example, right? But this is something that we must remember. We must match the degree of the polynomial essentially to the number of data points that were given. And once, I argue that once we arrive at this point of writing this matrix, we can breathe a sigh of relief and consider ourselves done. Why? Because we already learned how to solve the system of equations. For example, you've looked at Gaussian elimination. You have MATLAB code with the backslash operator that can solve for the unknown coefficients. Once you have these unknown coefficients, then all you have to do is plug this into the formula for the polynomial that you're trying to solve, and you can evaluate your function at any x. So if you like to produce then this green curve here that goes through the points, you can.